Now, let us see why this makes intuitive sense, right. Now, let us say I add, here is a network which has some node voltages and node currents, and branch currents. Now, let us say I add a current source into this node of value 0, right. Likewise, I am going to add another current source into that node with a current 0 and into this node with a current 0. What comment can we make about the node voltages and the branch voltages when we do this? Well, we are adding 0 currents into every node. So, nothing will happen to the node potentials, and therefore, nothing will happen to the branch voltages and to the branch currents, correct. Now, what I am going to do is derive this 0 in a rather special way, right. What I am going to do is recognize that 0 can be written as I2 hat plus I6 hat plus I1 hat is equal to 0, correct. So, what I am going to do is basically add a current here which is I6 hat, a current here which is I is I1 hat, and here going to add a current which is I2 hat. Okay. Likewise, in other words, I am going to replace, put in parallel with every branch in this network a current in the opposite direction and whose value is, where am I getting these currents from? These hatted currents basically are pertaining to the second network, all right. And please note that I am putting a current across every branch, right, but these currents are not chosen in an arbitrary way, they are chosen in a special way. What is so special about the way I have chosen these currents in pink that I have added here? What is so special about the way I have chosen those currents? Pardon? Yeah. So, basically all those currents basically satisfy Kirchhoff's current law, correct. So, even though I have added these new currents in pink, that is not what I have in effect done is added a current. What is the net current I have added at each node? Right. The current I have added at each node is 0. All right. So, nothing has happened to the branch voltages or the branch currents. Okay. In other words, I have replaced in the original network, if there was a branch, let us call this some EK, and IK is the current, EK is the voltage. All right. What we have done is in effect, in parallel with every branch, we have put in IK hat. All right. Now, this network is as legitimate as any other network, correct. So, energy conservation must be valid for, power conservation must be valid for this network too, correct. And therefore, what comment can you make about this branch? This is equivalent to, if you think of this as a branch, what is the voltage across this branch? Ek. What is the current through this branch? Ik minus Ik. Correct? So, what comment can we make about the power dissipation, instantaneous power in the entire network? Is simply K times sum over K, Ek times Ik minus Ik hat, all right. And so, this therefore, what must this be? What must this be? Well, energy conservation says that this must be 0. Well, this is nothing but must be 0. What do we know about this? This is 0 because that is energy conservation with respect to the original network, and therefore, it must follow that this chap is also equal to 0, right. Of course, if I just showed you just this result, it would be quite puzzling as to how you multiply the voltages in one network and currents in some other network, and how the sum magically turns out to be 0. I mean, if you go think about it this way, you see that it is not that surprising after all, right, because energy conservation must hold for this network, all right, and and we already know that this must be 0, so the other term must also be 0. So, Telegan's theorem is basically a statement of instantaneous power conservation, right, and that is physically appealing because you know that at any instant of time, if the total power consumed in some branches is not exactly equal to the power generated in other branches, then if that were true, then we would not all be sitting here, we would be selling power, right. There is a way of making more energy than you dissipate, and therefore, okay. So, that is the all right. Now, it turns out that Telegan's theorem has a whole bunch of interesting applications, and let me talk about a couple of them. Telegan's theorem can be applied to two networks of having the same graph, which basically means that there are a whole bunch of obvious things implied here. It could be applied, the second network could be the same as the first network, the second network could be the same as the first network, but at a different time. The second network could be completely different from the first network as long as it has the same skeleton or the same graph, right. Okay. All that this is saying is that Vk sum over all branches of Vk times Ik hat is equal to 0, which is the same as the sum over all branches of Vk hat times Ik, all right. And one example, all of you have seen taken an analog circuits class, and where all the network elements are nonlinear, correct, and what do you call, we know that analyzing nonlinear networks is difficult. So, we resort to, what do? We linearize the network and work with small signal equivalents, right, and the underlying basis for small signal equivalents are the following. I mean, you have some sources, and you change the sources by a small amount, and then you only write KCL and KVL for the incremental quantities, correct, and the basis for that is again you can think of it as a principle that we used while deriving Telegan's theorem. The original network, for instance, let us say you had some nonlinear element where the branch current and the branch voltage are related in some really nonlinear fashion. Okay? And remember that Kirchhoff's laws are not going to be, or the branch voltages and the branch currents are not going to change if you place in parallel with every branch an arbitrary current ik hat, where this ik hat is derived from another network. That other network is where this is the original network. The other network is where a particular source has been changed by some amount. Correct? So if you go and change say a source voltage by some amount, then all the branch voltages and the branch currents are going to get changed, and therefore this current is going to be Vk plus some delta Vk, and the current is going to be, you take a network and change one source, what happens? All the branch currents and the branch voltages change. So therefore this current is going to be Ik plus some delta Ik. Remember that these delta Vks and the delta Iks need not necessarily be small at this point, right? They change. That change is that capital delta. Correct? So what I am going to do is going to replace, those of you who have taken an analog circuits class have seen this before. But what I am going to do therefore is, in the original network, I am going to add a branch current in parallel, right, where I am going to call this Ik plus delta Ik. Correct? Does it make sense, people? Okay. Now, if I do this for every branch, what comment can you make about the branch voltages and branch currents in the original network? What comment can we make? By making this construction with the original network, what is the net current I have added at every node? Pardon? In parallel with every branch I have added Ik plus delta Ik. So what is the net current I have added at every node in the network? It is 0. Does it make sense? Because all these Ik plus delta Iks must satisfy Kirchhoff's current law. Correct? Okay. And likewise, what I am going to do is also replace, I am going to put in series with every node, every branch, I am going to put a voltage which is in the opposite direction. I am going to put Vk plus delta Vk. What comment can I make about what will happen if I put a voltage source of Vk plus delta Vk? Remember, Vk plus delta Vk corresponds to the branch voltage in that branch where I have changed a source, right? So what if I do this for every branch, what comment can we make about the net voltage that we've added in every loop? Well, we know that the branch voltages, are not some arbitrary branch voltages. They all satisfy this Vk plus delta Vk, therefore satisfy KVL, and therefore the effect of adding all these is that it doesn't change the loop currents, right? So therefore, if the original network satisfies KCL and KVL, it's apparent that this must also, if I replace every branch by this composite branch, it must also satisfy KCL and KVL. All right. So now what is the net voltage across this branch? The voltage across this branch is delta Vk, and the current through the branch is delta Ik. All right. I have flipped the picture on the right so that delta Ik flows in that direction, but otherwise everything is the same. Does it make sense, people? Right. So what is the moral of the story? This is telling us that if you have a network, if you have a nonlinear network and you change something, all right, well, all the branch voltages and all the branch currents will change. And this is telling you that the change in the branch voltage and the change in the branch current, right, okay, those changes also, if you form a network where you have network elements whose branch voltages and branch currents are delta Vk and delta Ik, then it will also follow KCL and KVL, correct? Okay. Now, the next assumption, so this is basically, it is true for arbitrary changes in the sources. All right. So, I'd like to reiterate that this delta Vk and delta Ik need not be small. The small signal approximation comes in when you assume that the changes are so small that you can relate the delta Ik to the delta Vk in a linear fashion. All right. So, therefore, you can see that the constructs that we used to derive Telegan's theorem in an alternative way also kind of throw light on why the small signal approximation is grounded in firm principles. It's right. The only approximation is this part, right. This is always true, right. So, the changes in the voltages and currents basically still obey KCL, KVL. The moment you relate the change in voltage to the change in current through a linear equation, that's when you have made an approximation, all right.